Hello everyone, this is Mr. V. Hill, and I'm here today to talk to you guys about functions. And we're going to be covering the definition of functions and some function notation here. So just to get some definitions out of the way, first off we need to start with the definition of a relation. And a relation is nothing more than a set of ordered pairs. And ordered pairs, of course, have one first coordinate, which we call the x-coordinate, and then the second coordinate is the y-coordinate. We're going to call the x-coordinates of these ordered pairs the inputs, and the y-coordinates are going to be the outputs. So every function is basically a machine, kind of, you want to think about it that way. We can input an x value, and it will spit out at us a y value. And so these ordered pairs, for our purposes, are normally going to be ordered pairs of numbers, which means that these ordered pairs are going to exist in this coordinate plane. Doesn't have to be that way. These inputs and outputs don't have to be numbers at all, but for Algebra 1 purposes, that's what we're going to be dealing with. Now, a relation happens to be a function if each input, meaning each x coordinate, is paired up with exactly one output. So every x gives us exactly one y. For example, let's consider maybe an equation like this. Y is equal to 3x. This equation, like we saw when we were graphing, this is actually the name we give to a set of ordered pairs in this coordinate plane. It has to be a straight line, and you can figure out what that looks like. Not a big deal for right now. But the point here is, this thing, if I tell you what x is, say 2, you can tell me what y is. If x is 2, y is of course 6. You get that one answer. If I say x is 5, you'll say y is 15. If I say x is negative 3, you'll say y has to be negative 9. We never get any confusion about that. So the big thing here is whatever x is, 3x can only be one thing. Therefore, it's a function. Okay? Now, as opposed to, let's consider a non-example here. Perhaps y is equal to the square root of x. Okay. Now, let's just say x is 9. Y is going to be the square root of 9. So, we'd say, well, if x is 9, then y is 3, right? Because 3 happens to be the square root of 9. But what about negative 3? If we square negative 3, we also get 9. So really, 9 has two different square roots, 3 and negative 3. So here we go. We have one input, which is 9, but that one input has two outputs. Therefore, it's not a function. Okay. Now, I'm lying a little bit here because the way we deal with this is we claim that this symbol is going to only specify the positive square root, but we'll deal with that later when we get to that. But in general, if we consider all possible square roots, this thing will not be a function because most everything has two square roots, the positive one and the negative one. Now, these equations, of course, we usually represent them as graphs, well, or equations, but we really want to get a handle on what the graphs are like. So, when we have a graph, we have a nice test to see if something is a function. And that test is what is known as the vertical line test. And so if we have a graph, we can tell if it's a function if any vertical line intersects its graph in at most one point. It might intersect in no points, depending on what the possibilities are for your x's. Sometimes we have to restrict that. But just let's look at those same examples that we were looking at last page here. So the example first we started off with was y is equal to 3x. And if you want to go through and make the table and all, you can, but the basic idea here is the graph of this particular equation is going to just look like a straight line. A fairly steep straight line, but it's a straight line nonetheless. So this would be the graph of y is equal to 3x. And now if we take any vertical line in this plane, we draw it in there, I'll do that in red just so you can see it, we'll notice that any vertical line can only hit this slanted line here for y equals 3x in just that one spot. Therefore, it passes the vertical line test, and therefore this thing is a function. As opposed to our non-example here, we'll call this 2, we'll call this 1, example 1, example 2. If we look at y is equal to the square root of x, and I'm taking all possible square roots, when you graph that thing, and I invite you to go ahead and do that yourself, what you're going to get is a nice little curve that looks like this, but also comes down here. And you may notice that shape, it's a parabola, but it's a parabola on its side. And now, if we draw a vertical line over here anywhere in the first and fourth quadrant, we'll notice that that vertical line is going to hit this curve in two different spots. Basically, whatever x value we consider is going to have the positive square root for the y value up here and the negative square root down here. Therefore, this line hits in two spots, which means it does not pass the vertical line test, and this thing is not a function. And you'll see that later on down the line in this year, we're going to restrict this and say that we're only talking about the positive square roots, which makes everything okay. All right, so that's the vertical line test. Now, one last thing we need to understand about functions for right now is we have a new kind of notation for these functions. Now, the way we've been writing equations is with an x and a y. Something like y is equal to 2x plus 5. Okay. And when we're doing this, we have an x coordinate and a y coordinate. So what we're really doing is we're thinking about this equation as giving us a set of points in the coordinate plane where we have our x-axis and our y-axis, and then the function itself is going to be the set of ordered pairs that is going to look something like this for this particular equation. It's going to intersect the y-axis at 5, and you can work out what the other points are on that. So, of course, this thing is just a slanted line here. If we draw a vertical line, it's going to intersect in only one spot, so it is a function. But now what we're going to do is we're going to replace this y with some new notation here. And we're going to call this f of x. If you want to just understand the bare bones of this stuff, f of x and y are the exact same thing. We could, in fact, just call this, instead of the y-axis, we could call it the f of x-axis. Perfectly fine. It doesn't really matter what name we give this thing. But we'll say that f of x is equal to 2x plus 5 now. So here's the notation that we're using when we want to focus on just the function as a set of ordered pairs. Here, we're going to focus on the actions being done to x. So this doesn't mean f times x. Normally parentheses means multiplication. Here, f is the name of the function itself, which in some sense is the set of ordered pairs. But now we're focusing on how we get from the x to the y value, kind of. Here, we take the x and we multiply it by 2, and then we add 5. That gives us the y value. So we can think of f, the name that I've given to this function. So f is the function being applied to x. In this case, f is basically the action of multiplying by 2 and then adding 5. So we're focusing on what's being done to x. Okay? Because that's really kind of the important part. Not to say that anything else is unimportant, but this is what we're focusing on in Algebra 1, Algebra 2, Pre-Calculus, and Calculus, is the function itself as actions. So just applying this notation a little bit here, we could say that f of 7, well, that's what we get when we take the number 7, we multiply it by 2, and then add 5. And we can simplify this, of course. 2 times 7 is 14, plus another 5 is 19, no big deal. Or f of negative 3, well, that's what we get when we take negative 3, multiply it by 2, and then add 5. Of course, 2 times negative 3 is negative 6, plus 5, negative 1, no big deal. Okay, so it's just some notation, but it's more about changing your perspective. When we use the x's and the y's, we're focusing on the points in the plane, the graph. When we're using this f of x notation, what we're doing is we're focusing on these actions, the operations that are being done to our independent variable x. Now, just as an aside, one of the reasons why this notation is so handy is we can do things now with the functions. So suppose we have a couple of functions. We'll keep that same f. F of x is going to be the actions of multiplying by 2 and then adding 5. So we take whatever x is, we multiply it by 2, and then we add 5. If we have another function, let's call it g. G of x is going to be equal to, let's say, negative x minus 4. So g involves taking something, making it negative, and then subtracting 4 from that. Now this is handy because now we can apply the function f not to just x, but how about to this function g of x. So we take g of x and apply the function f to that. Meaning we take the function g of x, which is exactly this, negative x minus 4. Now we're going to take that thing and we're going to multiply it by 2 and then add 5. So now we get a whole new function out here. And from there, if we wanted to, we could even simplify this. We would distribute in this 2. 2 times negative x is, of course, negative 2x. Minus 2 times 4 is 8. Plus the 5. And then we can, of course, combine our like terms here, and we get negative 2x minus 8 plus 5 is effectively subtracting 3. And now we have that if we first do g and then apply f to this variable x, this is what we get. So we put these two functions together, and we end up with the actions of multiplying by negative 2 and then subtracting 3. This is what we call the composition of functions. We'll work with that a little bit more in Algebra 1, but you're going to see it a great deal more in Algebra 2. Anyways, that's about it for function notation and the definition of a function. Hopefully you took some good notes, and we'll see you in class. Thanks for watching.